Stat 101, Examples Class 10, our first example, which we've called Income and Education. So this is a comparison of two populations. We have a simple random sample of 25 workers without tertiary qualifications, and another sample of 50 graduate workers who do have qualifications, graduate workers, so they will have tertiary qualifications. Now we have mean and standard deviation for each of these samples, the mean annual income for the workers without tertiary qualifications of $38,000 and standard deviation of $14,000. And those of the 50 graduate workers with a mean of $78,000 and a standard deviation of $24,000. Now we're asked here to use an alpha value of 0.01 to test the claim that workers without tertiary qualifications have a lower mean income than those with tertiary qualifications. So this is a test to determine whether there is a lower mean in the population for those without tertiary qualifications than there is in the graduate population. So our test statistic, when we're working this out, we're going to be taking the smaller of those samples, which is a small sample. Recall that small sample is when n, the size of the sample, is smaller than 30. We're going to be looking for a small sample test statistic here where we will assume unequal variances. That's our default if we're not given any further information about the population variances. So to begin this test of the incomes, we would begin by calculating the test statistic. We've got all the figures there from the samples. We'll begin by finding the test statistic before we go through our whole hypothesis test procedure. So the calculations we'll need here, the test statistic, which you can find from a formula sheet, is the t-test statistic. If you have a formula sheet with the test statistic using unequal variances, we're going to write that formula now. That would be t equals mean difference, so x1 bar minus x2 bar, minus the hypothesized mean difference, mean 1, population mean 1 minus mean 2. And on our course, that hypothesized population mean difference will always be 0. Now we divide this calculated difference in the means minus population mean difference divided by the standard error measure, which in this formula is the square root of S1 squared over N1, that's the standard deviation for the first sample, plus S2 squared over N2, that's the standard deviation for the second sample. Now, using our values from the previous slide here, we have mean 1, 78,000, minus mean 2, which is 38,000. So that's mean 1 minus mean 2, minus hypothesized mean difference, which would be 0. We're calling mu1, we're calling graduate workers here, and mu2 would be the workers without tertiary qualifications. That gives us a positive value for the mean difference. And we're dividing by the square root of 24,000 squared. That was the standard deviation for the first sample, divided by 50, that's the size of the first sample, plus 14,000 squared, divided by 25. So that's the calculated value for the standard error using this formula. Now, the difference on the top line there is 40,000. 78,000 minus 38,000, that's 40,000. And on the denominator here, check you can get these calculated values. We have 1152,0000 plus 784,0000. Those are the values for the squares of the standard deviations divided by sample size. And that denominator value there, when we've taken the square root, comes out at 4400. So our test statistic here, 9.09. Now that's a very large test statistic. We're used to test statistics having smaller values than that. So what on earth, have we done anything wrong there, or is this something that's quite unusual? So our test statistic here, 9.09. Now moving on to the next screen and using that test statistic, which we'll add in straight away so that you can see and we don't forget, the test statistic is 9.09 from the previous slide. Remember now, when we come to do our hypothesis test, we have a procedure whereby we go through and make it clear what our hypotheses are at the start. So we'll begin by writing down that population mean 1 is the tertiary qualification mean of values of those salaries. And mean 2, mu 2, is the mean of the workers with no tertiary qualifications. So now we have a definition for mu1 and mu2. Remember, these are population values. Now going back to our question in this problem, our question was whether the tertiary qualifications, people have a higher mean income than those without tertiary qualifications, which in the example was written slightly differently. We were looking to see if we were testing the claim that workers without tertiary qualifications have a lower mean income than those with tertiary qualifications. So in determining our hypotheses here, our first null hypothesis will be there is no difference. So that will be mean 1 minus mean 2 equals 0. No difference between the population means. And the alternate hypothesis in this example will be mean 1 minus mean 2 is bigger than 0, because that would mean that our population mean for tertiary qualifications would be bigger than the mean for the no tertiary qualifications people. Now in this example as well, we had an alpha value of 0.01 and degrees of freedom, smaller sample size minus 1 here. Our smaller sample was 25 workers, so 25 minus 1 gives us 24 degrees of freedom. We're using smaller sample size minus 1 for a conservative value for the T critical value here. So recall this is a T test statistic, and so when we're calculating the critical values, it's a one-tailed test. So we would be using here the T distribution where all of our alpha value, 0.01, is at the top end, the right-hand end of the distribution. So we can sketch our T distribution here. Remember, that would be a symmetrical distribution with 0 in the middle and all of our alpha value 0.01 at the top right-hand end. And this means that we would be finding our critical value either by using Excel or from the T-table. Now you can use the T-table with this number of degrees of freedom because we have 24 degrees of freedom, and that will be a figure that's on the table. So we'll go to the tables first. We have one here. Now looking at the T-table, and of course you can get these from the back of a textbook, or in this exam you'll have, in this course you'll have this in a formula sheet. So going down the left-hand side to 24 degrees of freedom here, and notice across the top we have two expressions, area in one tail, area in two tails. So we're looking at area in one tail of 0.01, and if we intersect that 0.01 column with the row for 24 degrees of freedom, then we can see the figure that we're going to use here, which would be 2.492. It's not letting us write on the screen. So that would be our value. Now we can also find this in Excel, but Excel, of course, has a requirement that we give in the TINV function a two-tailed alpha value. So the alpha value we had here was 0.01 in one tail. So to get the same value in Excel, we would need to be writing it with T INV, we need to put in 0.02. That's doubling that value. And the number of degrees of freedom, which is 24. So 0.02 and 24, which will give us the same value when we work that through, 2.492 from Excel. So the same value in Excel needs a two-tailed alpha value. So back to our problem. Now we have this t value for the critical 0.01 and 24 degrees of freedom of 2.49. However you find that, whether it's from Excel or from a formula sheet, this is the critical value which determines for us how to make a decision. And our decision would be reject the null hypothesis if our test statistic is greater than that critical value 2.49. So in this problem, we have sufficient evidence to reject the null hypothesis because our test statistic is way out over on the right-hand side there. So that was 2.49 for the critical value of t, and
there's 2.49. Is it 2.49?
it is 2.49. We saw it twice. And so we would reject the null hypothesis if our calculated test statistic is greater than 2.49. In fact, it's a lot bigger. So we have evidence here, and our conclusion would be, in the context, we have sufficient evidence, well, we have strong evidence, in fact, here, to suggest that workers without tertiary qualifications have a lower mean income than those with tertiary qualifications, which was our original hypothesis. So again, we have sufficient evidence to suggest that workers without tertiary qualifications have a lower mean income than those with tertiary qualifications, which is great evidence to suggest it's worth going to university. So finally there, one more time, that conclusion, we have sufficient evidence to suggest that workers without tertiary qualifications have a lower mean income than those with tertiary qualifications. And that's the end of example 1 on mean income.